radiation of wavelength lambda is incident on a photocell. The fastest emitted electron has speed v. If the wavelength is changed to 3 lambda by 4, then emitted electron will be. 4 options are given to us. And according to what is given to us, it is not even required to solve this problem. The reason is very simple. We know that the fastest emitted electron will have speed v, and hence it will have the kinetic energy mv square. Incident radiation has wavelength lambda. Now energy is inversely proportional to lambda. So that simply means that when we increase the wavelength, then energy will decrease and hence the speed will decrease. But if we decrease the wavelength, then energy will increase and hence the speed has to increase. So it simply means that if the initial wavelength was lambda and final wavelength is 3/4 of lambda, then we are reducing the wavelength. If we are reducing the wavelength, then we are increasing the energy. If we are increasing the energy, then definitely the final speed, suppose if it is v dash, then v dash has to be greater than v. So this should be the correct option in this case, without solving anything else in this case. But as a part of formal process, we will also see the method of getting this answer. We know that from Einstein's equation that energy incident in form of radiation, a part of that energy will be used as the work function for liberating electron, and remaining energy left will be used by the liberated electron in form of kinetic energy. So that making kinetic energy a subject of formula, we get E minus phi. Now we know that kinetic energy is half mv max square. E is equal to hc by lambda, and here phi is the work function. Making v as a subject of formula, over here we get twice E by m minus twice phi by m, and E can be replaced as hc by lambda as shown over here. So this is the equation that we get, out of which we find that 2h, c, m and phi, they all are constant. So we can put up some constants over here. Twice hc by m, let us say it is equal to constant k, and 2 phi by m, let us say it is equal to constant beta. We can very well notice that beta is a positive constant over here. The reason is that phi is a work function which is a positive value. Mass is never going to become negative. But altogether it simplifies our expression for the speed. We get v max square is k by lambda minus beta. Now two conditions are given as far as the wavelength is considered. So we can write initially v square is equal to k by lambda minus beta, and finally v dash square is equal to k by lambda dash minus beta. If we subtract these two equations, so v dash square minus v square is equal to k by lambda dash minus k by lambda, beta will get cancelled away during subtraction process. Further, we can see that lambda dash is equal to 3 lambda by 4, so putting up that value we get v dash square minus v square is equal to 1 by 3 k by lambda. If we see this initial condition, then we can also write k by lambda as v square plus beta. So this k by lambda can be replaced as v square by beta, and on doing that we can have a further simplification which gives us that v dash square is equal to 4v square by 3 plus beta by 3. As we know that beta is a positive constant, so this entire term is going to remain positive. We can write down v dash square must be greater than 4v square by 3, or v dash should be greater than square root of 4 by 3 into v. So again we come up to the same option, that is option A.